Hey everyone, this is a video lesson that I'm using in my AP Calculus AP class, and I'm putting online in case it would be helpful to others as well. There is a link to a printable set of guided notes in the description of this video that you can use to follow along with the problems as I do them. In this section, we are going to continue to look at definite integrals as area under a curve, and we're still going to use area formulas to calculate their values. However, we are going to look at the formal definition of integral, and we'll look at notation a little bit deeper. Okay, so let's recall something that we saw in the last section, and that is the LRAM approximation and the RRAM approximation for the function x cubed over the interval from 0 to 2. Okay, in the warm-up questions, it says, using the example above, which we saw in the last set of notes, which rectangular approximation underestimated and which overestimated? Now, I don't even think you need to have done those problems to know, just based on the pictures, you can figure out that the LRAM approximation is definitely an underestimate, right? And the RRAM is an overestimate. Okay, these rectangles are definitely under the curve and these ones are definitely over. So the underestimate was LRAM and the overestimate was RRAM. Okay, take a look at number 2. Could you say that LRAM is always an underestimate? That should say an. There's a typo that I've just been letting ride for years because I've used this set of notes for years. Okay, could you say that LRAM is always an underestimate and RRAM is always an overestimate? If not, give a counter example. I'm just going to tell you, no, LRAM is not always an underestimate and RRAM an overestimate. It is in this case, but that is because the function x cubed is increasing over the interval from 0 to 2. It's increasing everywhere, actually. But if we had a function that was decreasing, like this, the concavity actually doesn't matter whether it's concave down or concave up. If it was decreasing, for a decreasing function, LRAM would be an overestimate and RRAM would be an underestimate. And if you think about it, it would make sense that the left endpoint rectangles that we draw would go over because the left points are higher than the right, and the right would go under. All right, so, we know that MRAM and trapezoidal rule typically gave us much more accurate approximations, but is there a way to make LRAM and RRAM more accurate? And the answer to that is definitely a yes. Okay, what we could do, and hopefully you saw this in the last section, is we could use more subintervals. By the way, that would make your subintervals smaller, right? And finally, last warm-up question. What does this symbol denote in mathematics? Okay, you're going to see this symbol in the definition of definite integrals, so we want to make sure we know what it is. That is a summation symbol, right? It is it's a uppercase sigma. It's a Greek letter sigma. But what it means in math is to find the sum. Okay, so be aware of that. Okay, so these RAM, rectangular approximation techniques, they are called Riemann sums. And, here's just one more example of rectangular approximations that, again, we can just put the name Riemann sum to. You probably heard me say that before. Okay, so this is the function, the square root of x over the interval from 0 to 1. And it tells us that the rectangles below the curve are the left Riemann sum, and the rectangles above the curve are the right Riemann sum. The question is, which Riemann sum is more accurate in this example and why? Hopefully, you don't have to do much analysis to determine that the left Riemann sum I never think it's spelled with I before E, but it is more accurate. And the reason is that the subintervals are smaller, right? Or we could say we have more subintervals, more rectangles. Okay. All right, now that we got that stuff out of the way, it's time for the fun. Now, if you're following along in your notes packet, you can put what I'm about to do just like right underneath that example that we just did, or whatever you want to call that Riemann sum thing we just did, okay? Right above the box that says the definite integral of a continuous function, and we'll put that definition there in just a moment. But what I want to do first is I want to set up where the parts of the definition that you're going to see come from. And one way that I have found to do that is to set up a little table, just like we did when we were doing our approximation techniques in the last section. You know, whether you were doing LRAM or RRAM or MRAM or trapezoidal rule, you know, the way that I always set it up to organize the work is as a table like this. We would set up a subinterval, or all of our subintervals would go in this column, right? Now we're not going to set up a very long table, so you just need to draw a little line there. Okay, and then what else? We would look for the width of the rectangle. I guess I should say we're doing one of the rectangular approximation methods, or a Riemann sum here, not trapezoidal rule. Okay, so we would have the width of the rectangle. What else? We would have the height. Multiply those together to get the areas. Okay, so maybe I made my table too long. There we go. I just got really excited, that's all. Okay, so this is going to look a little bit different, though, than what you're used to seeing when we set it up in the last section. In the last section, we would set up subintervals here in interval notation, right, with like brackets. But what I'm going to do now is I'm just going to say, let's say we're working in any subinterval. It doesn't matter which subinterval. We're just going to choose one to work in. Okay, we're going to call that specific subinterval that we're working in the kth subinterval. It could be the first subinterval, the second subinterval, the third, the fourth, the fifth. Kth just stands for one of those subintervals. Okay, and then what we would do is we would look for the width of our rectangle, right? And it was the same as the length of the subinterval, or the width of the subinterval, we could say. But what I want to point out in particular, okay, let's focus on the left Riemann sum here, is that it is a distance along the x-axis. It is how far we are going on the x-axis. And so we could call that width delta x. Does that make sense? Okay, now the height. This is a little bit trickier to denote. The height would come from whatever point we were deciding to use, whether it be a left endpoint, a right endpoint, or the midpoint, plugged into the function. Right? We would choose, are we going to do LRAM, RRAM, MRAM? Okay, let's say we're doing LRAM. Oops, what just happened? My gosh. Okay, we're good. I thought I lost stuff, but we're good. It's just like my mouse is being crazy right now, I guess. Okay, let's say we're doing the left. We would take that left endpoint and we would plug it into the function to calculate the height, right? So let's call that point that we're using C, or in the subinterval, the kth subinterval, we're going to call it C sub k. I know that's weird, but that's just like, in this case, it's the left endpoint. Okay, plugged into the function, okay, this is the square root of x, but it could be any function. So plugged into the function, let's denote that as f of C sub k. Isn't that fun? F of C sub k, that's how you say that. When we looked at the intermediate value theorem, we saw something similar to that. I don't think it was C sub k. I think it was F of C equals k, but still, fun letter choice. Okay, and then finally, we would multiply these together, the width times the height, to get the area, right? Now, instead of writing that as delta x times F of C sub k, let's write it as F of C sub k times delta x, like that. It just shows that we're multiplying the height and the width to get our area. All right, now think about what we did after that. Like after we got all of our subintervals done, we went to the area column and we added them all up, right? We added up all of these values. So we can denote that in math with a, oh, that was so bad. There we go, a capital sigma. That means add up all this stuff. Add up all of these calculations. Okay, and we would say let's start with the first subinterval to the last subinterval. We'll just call the last subinterval n. You're going to see that in the definition of a definite integral, and I just wanted to sort of set up where it comes from so that it doesn't look so completely foreign to you. I hope this kind of makes sense. Where did this come from? The width of the rectangle times the height of the rectangle. Add it all up to get our approximation. Finally, think about how do we make our approximation exact? How do we get it to be exact? How do we eliminate the error? Okay, and if you read the wine barrel story, we talked about doing a limit, right? We make those, pieces that we are using smaller and smaller. And if we make them smaller and smaller, that means there's more of them. And so what we can denote that as here is a limit as n, meaning how many we're using, goes to infinity. And that's your definition for a definite integral. It's one definition. There's actually a couple of different ways you can see this. Usually when you look it up, you don't see this poor lettering choice here of F of C sub k. You see something else. Sometimes you see the limit as n goes to 0, or the delta x goes to 0. That would be the width going to smaller and smaller amounts. There's actually a couple of different ways to show this. Okay, but I like this one because I think it's fun. So here's your definition of a definite integral. Let f be continuous on a closed interval, and let that closed interval be partitioned into n subintervals of equal width. That delta x equals b minus a over n is just telling you the width that we're using for our subintervals. Then the definite integral of f over the interval a to b is the limit as n approaches infinity of the summation of f of c sub k delta x. Woo! Isn't that fun? Okay, if you need to pause this to write that down, go ahead, and then we're going to move on to talking about turning this craziness. I know, it looks kind of crazy scary. There's a limit, there's an infinite limit in there, there's this giant summation, and there's some bad word in here as well. Okay, we're going to turn it into a different notation, though, on the next page. Oh, wait, no, first, look at this. I did tell myself this was coming, and then I forgot. Now that you know the definition of a definite integral, you can understand this meme. Bad boy can hold an infinite number of f of x sub I delta x in it. Okay, that's another way to show area of the rectangles, and an infinite number of them, because we're trying to make this Riemann approximation an exact area calculation. So an infinite number of them does that. Yay! All right, now let's talk about notation. Leibniz, I think that's how you say it, I never remember. I think it's Leibniz, changed the integral notation from Greek to Roman just as he did for derivatives. So this, I just need to look at if I want to write this. Yes, this definition that we see here for definite integrals gets changed to this, okay, the infinite limit of the sum the limit of the summation gets turned into this S-looking symbol, S for sum, but it's like a stretched S. Okay. We usually have an interval here for a definite integral, but we'll put that on later. The f of c sub k is just going to get turned into f of x. And the delta x gets turned into, because it's infinitesimally small, we can write it as dx. Look at that. Isn't that much nicer than that craziness? Okay, and they mean the same thing. So now let's talk about this integral notation a little bit further. This S-looking symbol that you see here, stretched S, you can call that your integral symbol. So when you read these, you usually say the integral of, and then you read the lower, the left endpoint, or we call that the lower limit of integration. And then you read the right endpoint, which we can call the upper limit of integration. Next, you read the function, or we can call this the integrand, but it is the function that we're working with, the function that we're finding the area under. And finally, your dx, this x beside the d is showing your variable of integration. Okay, and that will become really important as you study integrals in, like, using integrals in differential equations and like double and triple integrals in multivariable calculus. There's so much fun to be had with your variable of integration there. Okay, so here's how you read an integral. You say the integral from a to b, if there are numbers here, of f of x, whatever this function is, dx. So what you see next in example 1 and the little you try are just some really basic examples of recognizing this stuff as the definition of a definite integral and rewriting it in integral notation. Okay. We have the interval from -1 to 3 is partitioned into n subintervals of equal length, delta x equals 4 over n. Let m sub k denote the midpoint of the kth subinterval. Okay, that just means that we're using MRAM here. Midpoint Riemann sum. Express the following limit as an integral. Okay, so we have the limit as n approaches infinity of the sum of all of this stuff. That is going to become, watch how easy these examples are, the integral of this function. Okay, all that stuff right there, we're done with it because it all becomes that integral symbol. Now we're moving on to the function. This function in x form is just 3x squared minus 2x plus 5. The dx will change to, or the delta x will change to dx. Finally, it does tell us the interval is from -1 to 3, so let's put those on as our limits of integration, and we're done. We did what was asked of us. It didn't even say to evaluate. It just said express the following limit as an integral. So we did. Now, we could evaluate that. We could talk about how to evaluate that, and we will as we move on through the rest of this chapter. Okay, so I would recommend at this point you pause the video and you try the little you try down here. Again, these are pretty simple. You're just rewriting from this notation into integral notation. Okay, and here's the answers. I showed two different possible answers. You probably have this one, the integral from 0 to 3 of 1 over 4 minus x dx. But I just want you to know that you could have that dx in the numerator, and it could look like that. Okay. Now, rewriting Riemann sums as integrals can get more complicated. Okay, there are some more complicated examples that we will see in some practices, but right now we're just talking about basics, and so just enjoy this while it lasts. Oh my gosh, and here's another meme. Look, I am just like full of, like, this is a surprise meme. I didn't even remember that this one was here. And I made this one a long time ago. When you can't decide whether you're a rebel or a nerd, you spray paint the definition of definite integral on a barn. There you go. Okay. Now, let's revisit the idea of integral being area under a curve. Okay, what do we mean by area under a curve? Well, first of all, keep in mind that what we really mean by that is area between the curve. What? And the x-axis. Okay, so for example, let's just draw a curvy function like this. And let's say we're trying to find the integral of the function from this point to this point, a to b. Okay. When I say area under the curve, it's the area from the curve to the x-axis, which would be here. When the curve is above the x-axis, it is under, but only to the x-axis, of course. But then when the curve is under the x-axis, the area is actually above the curve, right? It's up here. Now, also, what you want to keep in mind is that, we're working with heights, y-coordinates of our rectangles that are negative when we are under the y-axis. And so, because we have in this region negative y-coordinates, that means that this area would be negative. And whenever we find an integral of a function, what we actually call that is net area, meaning positives with negatives combined. Okay, so be aware of that. Oh no, told you, my clicking is weird today. Okay, so in the last few problems here in these notes, you are just looking at an integral and you are now asked to evaluate. But we still haven't talked about specific methods to do that other than just find the area however you can. So what you want to keep in mind is that these examples, you're going to want to look at the graph of the integrand or the graph of the function over the interval to determine what kind of shape do you have, and you're going to use that area formula to evaluate the integral. So for example 2, we have the square root of 4 minus x squared. And I'll just do a standard viewing window. Okay, that's what it looks like. And we are looking from -2 to 2, which is actually from here to here. Now, what you should recognize this as and this as is a semicircle. This is, a semicircle in a function form. And so what we're going to do here to evaluate this integral is we are going to say the integral answer is going to come from the area of the semicircle with what radius? That's what you need to know in order to find the area of a semicircle, right? With a radius of 2. And so the integral from -2 to 2 of the square root of 4 minus x squared dx is going to be equal to area formula of a semicircle with a radius of 2. Area formula of a semicircle is 1/2 pi r squared. So we will do 1/2 pi 2 squared. And that's 2 pi, right? Or approximately 6.28. Now, keep in mind, we do have two very easy ways to check our answer to be sure that we're right. Since I'm in the graph here, I'll review that graphical way. You can hit second trace. Option number 7 is your integral option. And then you need to give the interval or the limits of integration. Lower limit first, -2. Upper limit second, that's +2. And let the calculator do its magic. I like how it shades it. And there it is, 6.28. Yay, we did it. Oh, I don't know what's going on. All right. So once again, I would suggest at this point you pause the video and you do this U-try. I will give you a little warning. This is definitely not going to be a semicircle. So again, what you want to do is you want to look at this function over this interval and figure out what type of shape are you working with here. Okay, so I don't have the final answer here, but I did pause the video and I drew the graph. And I actually think for this example, if you plot the endpoints for this function, it helps to understand where the numbers come from that you need to use for your area of a trapezoid formula. Okay, that's what we have here. That's the shape that we have. We have a trapezoid. And remember, when we did like the trapezoidal rule, it's like a trapezoid where the bases are those vertical pieces. So, this is one of the bases and this is the other base. And if you think about the fact that this is the point 0, 5, then, you know that one of your bases has a length of 5. And this is the point 0, 2, I'm sorry, 6, 2. And so that means that your other base has a length of 2. What is the height? The height is the distance along the x-axis, which is going from 0 to 6, so it's 6. All right, so now let's use the area of a trapezoid formula. Area of a trapezoid, which is 1/2 times the height times the sum of the bases. 1/2 times the height, which again is 6, times the sum of the bases, which is 5 plus 2. Okay, again, where did this 5 and 2 come from? Up 5 units, up 2 units. It's just the y coordinates of your endpoints. Okay, so what's that? 21? 21? Yay. I didn't box this and it's kind of bothering me. Look at that thick box. Okay. And finally, once again, I'll review the other way that you can check your answer. You can, if you're not in the graph, you can still do an integral calculation by doing the math button and then option number 9. And what you do here is you type in your function, then always comma x, that's like the dx, and then always comma the lower limit and the upper limit, comma the upper limit. And there it is, ta-da, the answer is 21. Okay, for example 3, we are going to use the fact that the integral from 0 to pi of sine of x dx is equal to 2 to find the answers to these other integrals. So you have some space here because I think it would be a good idea to draw the sine wave. Put it here more in the middle. And let's see, I'm just going to go from -2 pi to 2 pi. And I'm going to try to draw a nice sine wave, okay, not just like a sketch. So this is like -pi/2, -pi, -3 pi/2, and -2 pi, and then pi/2, and so on. This is +1, -1. Okay, sine of 0 is 0. I just always start there. Sine of -2 pi is 0. There's another 0 right there, right? And let's see, it's +1, -1, +1, -1, 0, -1. Oh, I'm doing all of these in black and it's not standing out because that was silly of me. Let's do that color. I should have paused the video to do this, but you know what? It is what it is. Ta-da! And it goes on. That's pretty nice. Okay, so again, we're looking at the interval from 0 to pi, and it's telling us that the area of that space between the curve and the x-axis is 2 square units, is 2. So can you figure out what the area is on the interval from pi to 2 pi, this space? Well, it's the same shape, but it's below the x-axis, right? So it is just -2. Now, I usually have students get really excited about this when we do it in class, and they're like, wait, I can figure out all the rest. I know how to do this, okay? And so I tell them, just go, do it. So if you want to do that, just stop listening to me and just do it on your own. Go for it, okay? Because this is kind of fun. It is kind of fun here. Let's now do the integral from 0 to 2 pi. 0 to 2 pi. Well, that's a +2 with a -2. So that net area is 0. By the way, you can check all of these answers using like the Math 9 in your calculator or Calc 7, right? All right, here we're still on the interval from 0 to pi like we were here, but we have this constant 2. We haven't formally said this yet, but there is something called a constant multiple rule, and that just says that you can take a constant multiple times an answer that you already know. So what I'm trying to say here is you can just do this 2 times that 2 to get an answer of 4. Okay, -pi to pi. -pi to pi. Well, that's a -2 with a +2, so that's 0 again. 0 to pi over 2. What's that? Well, that is just half of the shape, so the answer is 1. Now, you have to be careful. You cannot always assume that half of an interval, these bells are driving me nuts. You can't always assume that half of an interval is going to be half of the integral answer. However, because there is this line of symmetry at pi over 2 and you have the same area on each side, you can take half of your answer there. Okay, finally, try this one. It's really fun. You're going all the way from -pi over 2, which is right here, to 2 pi, all the way over here. Okay, so think about what all of that would be as net area. Are you getting -1? You have a -1 area right here, +2, -2. These pieces cancel, so your final answer is just -1. Oh, wasn't that fun? Keeps advancing too far. Okay, there we go. Example 4. Finally, I think this is the last example. Find the integral from -1 to 2 of the absolute value of x over x dx. All right, so again, what we're going to do with this one is we're going to look at what does this look like as a graph. What shapes do we have here? I need to get my absolute value. X over x is 1, right? But when you throw that absolute value in, it's going to split into -1 and 1. Like that, right? 2 horizontal pieces. And there is a discontinuity at x equals 0. However, you can still integrate over that discontinuity because what we can do is split it up into the area of this part and the area of this part, which is what we're going to do here. Okay, so I'm going to sketch this. I'm going to actually pause to sketch it. Okay, and I only sketched over the interval that I'm looking at here from -1 to 2. So what I'm really doing here is I'm finding the area of 2 rectangles. I'm finding the area of this rectangle, which is a -1 right? It has a height of -1, a width of 1. We're going to add to that this area of this rectangle above the x-axis from 0 to 2, which has a height of 1 but a width of 2. And so that gives us a net area of 1. Okay, when you do that one in the calculator, let's see what happens. I don't remember what happens, actually. This will be a surprise. It doesn't give you an error. I didn't think it did. It gives you the answer. It gives you a not exactly 1, but an approximation, and that's just because of the program that the calculator is using. Okay, everybody, that is it for this set of notes. I hope this was helpful in furthering your understanding of integrals. Bye.